So welcome everyone to this special Colloquium event. So we decided that, since we're having remote events anyway, let's have a remote event just before the holiday season. So let's talk about physics and the holidays. Normally we would have a Faraday lecture at this time of year. So in some sense, this is the far away lecture. So we're a set of faculty members have prepared different pieces of the story of how Santa is a physicist. I should start by pointing out that, even although this is a digital meeting, we acknowledge that the UBC Vancouver campus is on the traditional, ancestral, and unceded territory of the Musqueam people. And we encourage attendees to learn about the history and culture of this land and honor its original inhabitants. One of the cool things about the Musqueam people and the Coast Salish people in general is their language. And I'm by no means an expert, but I'm led to believe that this is Ias Christmas is effectively the local version of Merry Christmas. So if you haven't learned anything else today, you learned at least one phrase in the Hunkamanum or Hulkamanum language. So the idea here is that we're going to talk about the physics of Santa. At the end of the talk, we're going to encourage everybody to wear appropriate attire or stick up a background that's appropriate. And I know not everybody celebrates Christmas in the same way. So whatever your holiday tradition is, to try and encourage you to do that, I'm going to cover up my Santa thing here. Hold on a sec. Okay, so there we go. So that's better, more Christmassy. So how does Santa accomplish this feat where he delivers all these presents in a 24-hour period to children all over the world? And the obvious explanation is that he uses advanced physics techniques. So we'll be telling you about how Santa is really a physicist. To do that, we're going to split into 5 basic topics. So there's going to be 5 questions that we answer. So first of all, do the reindeer actually fly? The second question is, in order to get around all the houses, does Santa have to travel really fast? So does he use special relativity? Thirdly, does he even go beyond that and use curved space-time, so general relativity and black holes and so on? Does he use the second main breakthrough in 20th century physics, quantum mechanics? And lastly, how does he deal with all those toys? So does he use, or do the elves use nanotechnology in order to make the presents? So first of all, I'm going to hand over to Chris Waltham, who's going to start us off with the first topic, which is, do the reindeer fly? It's all yours, Chris.
Thank you. Yeah, so Douglas asked me to give a talk on what makes reindeers able to fly. Now this requires, for those of you who remember the Nixon years, this phrase cognitive dissonance. But hey, I have had a university education, and if university education teaches anything at all, it's how to deal with cognitive dissonance. So what do you do first when you ask a question like that? Well, you hit the books. And one of the best of them was written by Boyer Alborn from our department, zoological physics. But amongst the 3 most thumbed books in my bookshelf include a scaling book by Knut Schmidt-Nielsen about animal size and why it's so important. And the third one is a beautiful little book called The Simple Science of Flight by a Dutch aeronautical engineer, Henk Tennekes. So what does that tell you? Well, it's this picture here from Schmidt-Nielsen's book, which shows you the energy cost. The energy cost, in this case, per gram, per kilometer, that's the energy cost for an animal to move a gram of itself per kilometer in calories, and on the bottom is body weight here. And you can see flying is actually less than running by considerable margin. Flying is more efficient than running is. And not only that, it gets easier the bigger you are, because this is sloping downwards. The bigger you are, the less energy cost per unit mass to fly from A to B. It's easier to fly than to run. It's even easier to fly than to walk. Now, the flying and walking is not that dissimilar, but flying in any case is way faster. So if you can do it, you fly. Now, for the physicists amongst us, there's a very simple way of figuring out how much energy you need to fly, and it's just by considering this thing called the glide path. It tells you how much energy you would lose if you were gliding, and how much energy you would need to maintain your level flight, put in either by your muscles or by an engine. And that works out to be a mere 2 joules per kilogram per meter. Walking is rather more, and that, I believe, works out to be about something less than a calorie per kilogram per kilometer. Running's way worse. And all I put into this flying equation was simply g, acceleration due to gravity, the glide slope of any big thing. Any big thing means anything bigger than a wandering albatross. Anything up to a Boeing 747, pretty much the same. And here's a typical mechanical efficiency of either a human body or a jet engine. It's not that different. So the problem is you have to fly. If you want to fly, you have to go fast. And the power requirement is quite great, even if the energy cost is low. In other words, the energy to get from A to B flying might not be that great, but you have to do it at such a rate that that might be prohibitive. Mechanical power generally seems to be limited to about 10 times our basal metabolic rate. And basal metabolic rate is the rate at which you have to convert food energy into the workings of your body just to keep things running at all. And we seem to be able to put out about 10 times that in mechanical power if we're running or attempting to fly. That's determined by size. Now, this the bigger you are, the more you need, but it's not quite proportional to the mass. If you double the mass, you don't need to double the metabolic rate, and you don't have double the amount of power available. So bigger animals, kilogram for kilogram, have less power available than smaller animals do. And if you want to know the reason for that, it's to do with surface area and mass. Now, what speed you need to fly? Well, here's a bit of aeronautical engineering here, a little bit of physics of flight. You've got two sorts of drag when you try and fly. One called parasite drag. That's the thing anybody on the bicycle experiences that. That's what makes it harder to go faster and faster and faster. You can feel that the wind going past you. That's parasite drag. Plainly, the faster you try and cycle, the bigger that is. And that's the upside of this curve here, velocity versus drag. But then you have something called induced drag, which comes, if you want to fly slowly, you have to fly nose up. And that means the lift vector is pointing backwards, and that contributes a lot to drag. So this is this falling curve here. So it's actually harder to fly slow. Now, at some point here, there's a sweet spot where these two things cross, and you get a minimum total drag. Now, this is an equation here for the speed of this minimum drag. I'm not going to go into the individual components of that, but suffice to say, you can see it fairly easily if you consider this is weight and this is wing area. Then you can pretty much soon get to this idea that the flight velocity is proportional to mass to the power 1/6, which means it's going to get bigger the bigger you are, but not by a huge amount. So if you double the mass, you certainly won't double the flight velocity. The next question is that, now that was how fast you need to fly. Now we want to know how fast can you fly? Now it turns out that for a given glide slope, the power is force times velocity. Power available is this proportional to mass to 3/4. So the maximum available speed is just 1 over the other, and that's mass to the minus 1/4. In other words, going down. See the amount. So what this is called your metabolic velocity. This is how fast you can fly for a given mass, and that's going down with size. And if you put all this lot together, as Roy Alborn did in his book about zoological physics, now he's done a remarkable thing here. He's taken anything from fruit flies and midges all the way up to Boeing 747s, and he's plotted the mass, that's the weight of the thing, over many orders of magnitude, and this is the velocity. Now, the dashed line is how fast, sorry, the dotted line is how fast you need to go to fly. And that, the bigger you are, the faster you are. Boeing 747s have to go faster than crane flies, for example. And the dashed line is how fast you're able to fly. And you see these things cross here. So at this point, at about 15 kilograms, animals generally don't have enough oomph to fly. And that's about the heaviest birds you see. Wandering albatrosses, mute swans. After that, mechanical things have to take over. So where do reindeer come in this? Well, they fall rather embarrassingly short of the dotted line, how fast you need to be able to go. So they come, sort of 100 kilograms or so. And so they're a little bit short of the oomph. They can manage about 50 kilometers an hour, but to get off the ground, you need 100 kilometers an hour to fly for that weight. If you were a normal bird shape, but of course reindeers are not normal bird shape. So let's look at the company that reindeer keeps. There's obviously things in that region that can fly. Reindeer are sitting here in the red, and these other things, but notice these two schleikers, these are gliders. The human-powered airplane. Now, the human-powered airplane had extraordinarily long wings. In fact, all these things here have much longer inner wings than birds do. Yeah, I know reindeer don't have very long wings, but these are details. It's sitting in a range where things do fly. So it's obviously not impossible, but maybe we're going to have to deal with some physics other than this classical physics to make it all happen. But however iffy reindeer may be when it comes to pulling sleighs and like, one thing I can tell you is that when it comes to pulling sleighs, raccoons are absolutely rubbish.
Thanks, Chris.
So that one went down like a lead zeppelin.
I suggested.
I see some claps here. Thank you. Thank you, Jeremy.
No, it was very good. To carry on, it's over to me now. So let me fire up that again. Sorry. So to go to the next question, how fast does Santa travel? So let me just take you through some of the physics of this aspect of how Christmas works. So obviously he has to go pretty fast. So just how fast is that? So let's start with a little calculation about how many places does Santa have to visit. So I'm going to do very rough numbers here. Starting off with some precision, there's almost 8 billion people on the planet. There's almost 3 billion households. There's an average of 2.5 children per household, so you get about 2.2 billion children. What fraction of the world celebrates Christmas? Well, that's a very complicated question. There's a whole Wikipedia page devoted to that if you want to discuss the details, but it's approximately a half in some form or other. So you're looking at basically 1 billion children in something like 500 million locations. So you have to get around 500 million locations. Of course, not all the children will have been good. So some of them will be getting a lump of coal, and that's maybe easier to deliver, or they just get a little note telling them to get their own piece of coal. But either way, you need to get around about 500 million houses. How do you do that efficiently? So figuring out how to do that without wasting a lot of time, well, computer scientists call that the traveling Santa problem. And there's been a huge amount of research devoted to figuring out how to do that. Solving it is genuinely hard. It's technically hard. There are phrases for how technically hard it is that we don't need to go into. And the reason it's technically hard is because the combinatorics, the number of different possible routes, involve figuring out numbers like 1 billion factorial. So remember, factorial means I take 1 billion, I multiply it by one less than 1 billion, so 999,999,999. I multiply that by 999,999,999,998, and I keep multiplying by all the numbers until I get to 3 times 2 times 1. That's a very, very, very big number, too big to store on a computer even. So, you know, classical computers can't do this, but it's obviously a perfect problem for a quantum computer. So for quantum computers, you need physicists working with computer scientists. So obviously, the only way Santa can figure out how to do this route is that he has a giant computing farm. He's going to need to keep that cold, so he probably keeps it in a cold place. So that makes sense. He's going to need updated information because there's going to be, you know, new children being born, and people are going to have moved house, and all sorts of other things, complicated things are going to happen. So he's going to need to communicate in real time. It probably makes sense to have a Wi-Fi device near the front of his entourage. So it probably looks something like this. So that, you know, that the computing power required explains at least a couple of things Santa's going to have to do. But then how, you know, how fast does he have to travel? It's a lot faster than we think that the typical reindeer can do, actually. So a simple calculation you can do is just take the surface area of the Earth, divide by the number of houses you have to visit, and that's approximately the average distance between houses. And then that gives you about 1 kilometer. There's about 1 billion houses, so you need a path that's complicated, moves all around the Earth, but has to be about 1 billion kilometers. With, you know, this coefficient C, depending how good his quantum computer is, for whether he's got close to the optimal solution. There's slightly more than 24 hours in Christmas Eve. If you start in the east and work your way west, you can get 30 or maybe 31 hours, depending which one you start in, to complete the trip. But nevertheless, it's essentially a day. So the average speed you can work out is just the total distance divided by the total time. So it's about 10,000 kilometers per second is required just to do that trip. So that's pretty fast, and has required Santa to know all about Newtonian mechanics. And it's easy for Santa to know about Newtonian mechanics because he's old, so he can just ask Newton. And Newton, of course, has a direct connection to Christmas because he's one of the best known people outside the Prime Minister of Canada, one of the best known people to have been born on Christmas Day. So presumably Santa has talked to Newton for the last several hundred years. That speed is achievable, but it gives no time to actually deliver the presents. So you're going to actually have to stop in each house, and as well as delivering the presents, you're going to have to drink the milk and eat the cookies. You know, maybe you just drink the milk to save time and waistline, but whether you only drink the milk or eat the cookies as well, you're going to need, you know, maybe at least a second. Even the fastest speed eating contests actually takes time to ram the cookies down. So let's imagine Santa takes a second in each house, then he's going to have 1 billion seconds in order to visit all these houses. But there's only about 100,000 seconds, 10 to the 5 seconds available in those 30 hours. So he needs to somehow gain a factor of 10 to the 4 in order to be able to have enough time to leave the presents and consume the consumables. So the way that he does that is through special relativity, obviously. So because of the principle of relativity, moving clocks run slow. And here's an animation that I got from the Wikipedia page on time dilation. They're obviously thinking about the Santa problem here, because Santa is the one in red and the Earth is the one in blue. So as Santa goes round and round the Earth on this complicated route, time passes slower for Santa. And if he can do that fast enough, then he can gain this 10 to the 4 factor. So in fact, you can work out that he needs to just travel at 0.99999999. Did I do enough nines there? 5 times the speed of light. So he doesn't quite have to go at the speed of light, and then there's enough time in his frame to be able to deliver all the presents. And that means obviously that Santa also has to know about special relativity, relativistic mechanics, as well as classical mechanics, which he gets from his old friend Einstein, who he must have known, 100 years ago. And Einstein, just for the sake of the holiday spirit, I should remind you that he left us, of course, his famous secret message, MC squared is E, which of course means, Merry Christmas to everyone. That's obviously what he meant. So all that Santa needs to do in order to deliver all the presents in time is develop a relativity drive. And provided he can go at 0.895 of the speed of light, then it's easy. So it's the only thing he needs to achieve, and then there's plenty of time to deliver a presents. Of course, this isn't the only piece of physics available to Santa. So he's going to be able to rely on understanding other parts of physics in order to achieve that that goal. So what else can Santa do to achieve this Christmas present delivery method? And I'm going to try and.
Hi, I heard you were discussing the physics of Santa, so I thought I'd drop in. But I should warn you, my expertise is in molecular immunology, not physics. Unless, of course, this event is about that other Santa. People are often getting us confused for some reason. Sorry about that. But in any case, happy holidays, everybody.
Okay, so thanks to the president of UBC for helping us out there. Jeremy.
All right. Well, I like Douglas. Douglas explained, Santa doesn't have to go very fast, but in his calculations to reach every house, but he has to go really fast if he's going to drink the milk, but it didn't leave any time for eating the cookies. You can't really have all those cookies in a second, really. And so how does he do that? How can he make time for cookies? So it turns out, how can he make time for cookies? He can make a time machine, of course. That's what Santa can do. And it turns out that a physicist named H.G. Ellis invented a time machine. And here's the only picture I could find of H.G. Ellis, and it's kind of suspicious, isn't it? A resemblance there, but there's H.G. Ellis, and he used general relativity to do it. So I'm going to explain how Ellis discovered this time machine, and maybe someone else has used it for a long time. So this will give Santa a lot of time to go through the route all in that 30 hours and still have time for cookies. So this involves general relativity, and the basic idea is you could take two parts of the universe and connect them with a little tunnel. And what this tunnel was called, this first one that he calculated, was called a drain hole. And I know you've probably all heard of wormholes, but what a drain hole means is it actually kind of pulls you through it in one direction. You could go in the other direction if you want to. It just takes effort. Santa likes that he just kind of will flow through the drain hole from one end to the other. And this is how Ellis came up with it. And, those people who are into relativity, this is the Einstein tensor. We saw Einstein's picture there. And this is a scalar field, something in the universe, and that that is relatively ordinary, but to make this work, to make an actual drain hole that you can go through, that you had to put a little minus sign in front of there. And, you know, maybe we can't do it, but perhaps Santa is such a good physicist that he can make this work, and he can put a little minus sign there. And if he can do this, he can do a whole lot. So let's see what one of these looks like. And here's the idea that, you know, we live here on this surface, let's say, and these little blue lines are paths that you can take. And, you know, these paths kind of approach and then go away. You could be on the other side and come through and come back out again. And what Santa does is he takes this end of this drain hole. Oh, these little arrows mean that this is the side. Like if you just do nothing, you don't try hard, you'll flow right through and come out the other side. But what Santa does is take this end of the drain hole up here and moves it really, really, really fast, like Douglas was describing. And the time will go slower for this fast moving drain hole. It doesn't have to go that fast for Santa to get what he needs done. He gets this drain hole and he spins it around for about 2 hours and 40 minutes at 80% of the speed of light. This is one way Santa can make it happen. And we can do this calculation like Douglas is, how much time elapses at this side versus this side. This end isn't moving. It takes 2 hours and 40 minutes. If we do the math, on the other end, only 1 hour and 40 minutes elapses. So one end of the drain hole, over here, it's 1 o'clock. At the other end of the drain hole, it's 1 hour earlier. It's 1 hour earlier. So how is Santa going to use this for making Christmas? So, so the idea is if you go through the drain hole from this end to that end, you'll end up 1 hour earlier than you started. So let's say you're over here and it's 1 o'clock, you'll end up over here, wherever that end of the drain hole was, 1 hour earlier. So here's a picture of what it looks like. This is how Santa has set up this drain hole in Tübingen, Germany. And this is where it's set up in the summer, so he can dash from work in the physics department over there, go through the drain hole, and he's on the beach in Normandy. I mean, you know, I would have chose Cannes, you know, on the south of France, but Santa likes the chilly ocean for his beach time. So this is what's happening in the summer. Now, how does he use it on Christmas Eve? How does he actually do this? So here he is, Santa, and he's gone out and he carries both ends of the wormhole, the drain hole, along with him. And let's say he's delivered a whole bunch of presents, eaten a whole lot of cookies, and it's 1 o'clock. He goes 1 o'clock in the morning, and he follows one of these geodesics here through the drain hole out to the other side. And over there, he's now, it should say midnight. The clock got messed up, sorry. And if you're thinking about it, when he's over here, he's back where he was 1 hour earlier. And so he's going to meet up with himself 1 hour earlier. And then this Santa goes off and does the route that this Santa just did. And this Santa goes off and does something else. And they figured out, like, where should they all meet up every hour to make it logistically most efficient. And it turns out someone else solved that problem. And this is actually in Memphis, Tennessee at the FedEx depot, because that's the fastest place to get packages everywhere in the world. So here comes Santa, and now he's delivered an hour's worth of presents, except now it's midnight again. So then he goes off and delivers some other presents and then repeats again and again. So he's time travel Santa. So we've seen time travel in a lot of movies, and you have to figure out, well, if Santa's going to deliver all the presents in one night to everybody, time travel has to happen in a certain way. And probably a lot of you are familiar with these movies, and a lot of the movies you go time travel forward or backwards, and you end up on a different timeline. But if Santa's going to deliver all the presents, it's the Harry Potter style of time travel that Santa does, where he ends up back and meets up with himself, except unlike in Harry Potter or in where they in the big scene, he does it again and again and again. And in fact, there's millions of Santas just on Christmas Eve delivering presents. So Santa really has a really long day having to do this, just like Hermione does in Harry Potter when she goes to all the classes every day. So that's how Santa solves the cookie problem, how he manages to make time for cookies on Christmas Eve.
Thanks, Jeremy. Can we turn to James now? And again, if people have questions, feel free to post things in the chat, and speakers should have an opportunity to respond. James.
Ho, 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 Santa Claus here. Doesn't quite know the technology yet. Replacing James Charbonneau. Decent fellow, but not up to the task. What task, you say? The physics or the quantum mechanics of Santa Claus. So, we've established flying reindeer, relativistic Santa, wormhole Santa. For now, we're going to talk about quantum mechanics. So we all know that Santa gets around using the relativity drive invented by Sir Arthur Elphington. Unfortunately, this is the only picture, well, supposed picture of Elphington that exists. A competitor of his burned all known pictures. So this is some guy that sort of looks like Elphington. But what we know is that Santa dilates time and contracts space to get around and deliver all of his presents. But first, I'd like to talk a bit about some of the strangeness of quantum mechanics. And in order to do that, I'd like to talk about the Stern-Gerlach experiment, and particularly starting with the classic Stern-Gerlach experiment. In this case, we have an apparatus with a non-uniform magnetic field. And we have tiny little magnets that we can shoot through this field. What happens? Well, we shoot this little magnet through the field and it gets deflected upwards. We flip the magnet upside down and we shoot it through and it gets deflected downwards. We put the magnet on its side and it goes straight through and hits the middle. We tilt it a little, it goes a little down. We tilt it a little up and it goes a little up. And we repeat this experiment over and over and over again. And we get a smudge on the screen. Now consider the quantum Stern-Gerlach experiment, where instead of using a magnet, we use a spin half particle, say a silver atom, and we shoot it through this apparatus. We shoot it, the spin up goes up, the spin down goes down. Well, what about the sideways spin? We find something very peculiar. It doesn't go in the middle, but goes down. Let's try again. We shoot it and it goes up. In fact, if we take randomly oriented spins and shoot them through this over and over and over again, we find that it only ever goes to these two regions. And even a spin that is slightly tilted upwards could appear at the bottom. So repeating over and over makes these two distinct regions instead of a smear. So what we can do is describe the state of this particle in terms of a quantum superposition of some amount of spin up and some amount of spin down. And when you shoot this particle through the apparatus, a measurement is taken. And when this measurement is taken, according to the classic picture, a Copenhagen interpretation, the wave function collapses and we measure up. And the probability that we measure up or say measure down is related to the coefficient in front squared. But this is a very brutal process. It's discontinuous. It doesn't obey the Schrodinger equation. It's not unitary. So we have another interpretation. The many worlds interpretation, introduced by Everett in 1956, considers that not only is the spin a quantum system, but the apparatus and indeed the environment around is also a quantum system. And the whole environment, the whole apparatus, all obey the Schrodinger equation and evolve as such. So when a measurement is taken, instead of one spin disappearing and the other being the measurement, the apparatus and the spin become entangled, right? The spin up is associated with the apparatus that exists in a superposition of measuring spin up. And the spin down exists with the apparatus that exists in a superposition of spin down. And then slowly, over the multitude of interactions, the systems decohere and you get two universes, one in which we get spin up and one in which we get spin down. Some sloppy notation there by Santa. Should be all up arrows on the left one. But what does Santa care about this? Santa only cares about cookies and milk. And as such, we've talked about the cookie and milk problem is a difficult problem to solve. I don't have much time, so do I drink the milk or do I eat the cookie? Well, with this many worlds interpretation, I can rest assured that if I drink the milk in my universe, there will be a Santa in another universe that gets to eat the cookie. But back to life, this grim life without the relativity drive. An industrious Santa without the relativity drive might be able to cover a single neighborhood. But there exists a universe where I have a twin, and maybe me and my twin can cover 2 neighborhoods. There even exists a universe where I have 7 twins, but that's pushing the limits of biology, isn't it? So let's think of another way. What if I lived in a universe where I had the time turner from Harry Potter and the Prisoner of Azkaban? Not allowed. Though we saw how certain time travel can happen, the time turner itself runs on magic, not physics. The only universes are allowed are statistically improbable, but not physically, violating ones are not allowed. So I turn to the most preposterous universe, if you will. Imagine a universe where a cabal of Christmas elves ingratiate themselves with millions of families and over hundreds of years I just can't. It's too preposterous. It's too crazy. Thank goodness for the relativity drive, and Merry Christmas to all, and to all a good night.
Thanks, James. So to conclude our 5th part and get your Santa hats and holiday-esque backgrounds ready for the gallery view after this, but to conclude, we're going to turn to Steve Plotkin. So Steve, it's all yours.
Okay, hello and happy holidays, everybody. Today I'm going to continue with the physics of Santa, part 5, and the problem of the manufacture of toys. This is of course not about our own Santa, nor is it about the inspiration for Santa, St. Nicholas, the patron saint of sailors and merchants and brewers, woohoo, and some other ignoble professions, but students in various cities and countries of Europe. But this is going to be focusing on the Santa we've come to know and love, rendered here by Thomas Nast back in the 19th century, and an image depiction which is modeled after Bacchus, the god of revelry. So this is going to be this talk is going to be an example of Occam's razor in physics. Actually, it's not. It's going to be basically the opposite of Occam's razor, or Occam's duct tape, where we have a premise that we know must be true, and we have to find physics explanations to explain it. And the first thing we realize about Santa is he is a master of surveillance. He has the kind of surveillance infrastructure that would make Big Brother blush. If he knows you've been sleeping or awake, or bad or good, etc. He certainly knows what's on your wish list and what your parents didn't get you. And so he knows exactly what present to bring. He does this presumably by a supercomputer mainframe that's powered by sub-iceberg tidal generators. It really can't be windmills or something else we would see with satellite views. The cooling requirements, basically, they have to be the main reason that his base is in the North Pole. Otherwise, why would you want to live there? You can simply open the window and circulate air and cool the computers. So it all makes sense when you think about it. The information of what present to bring is certainly known. A problem, as we've seen, is how to get it there and how to have it ready-made when you're opening presents in the morning. So Santa by the numbers. This is what must have been a labor of love that's appeared in the Atlantic, calculation that shows that there's about 500 million families that would be celebrating Christmas on the 25th. And Santa needs to deliver presents to all of these. And can you see my pointer now? I don't know if you can see my pointer or not, but if you see on the top right, what it's shown here is a cumulative distribution up to those 500 million children that Santa must deliver to as a function of longitude. And you can see that there are some regions in longitude where he's going to be very busy, a lot of houses to deliver to, other regions where he gets to take a little bit of a break. But not much of a break, because at 22 million kids an hour, that's 365,000 kids a minute, or 6,100 per second. For Santa, totally doable. Santa needs to deliver these presents at a frequency of about 6.1 kilohertz. So our 6.1 kilohertz Santa is in, if we take these numbers seriously, he's in each house for a fraction of a millisecond. Subliminal messages take several milliseconds to register. The time constant tau for conscious perception is about 10 milliseconds. So no wonder we haven't seen him. But there's a problem with that, in that there's lots of anecdotal sightings of Santa. And so this estimate is naive because of wormholes or drain holes that have been previously mentioned, giving Santa extra time at each of these locations. You might ask, why not send, why send Santa through it all? Why not just send the presents through the wormhole? Seems sensible, but it contradicts the numerous incidental sightings that we have seen in Santa in our living rooms and taking off from the roofs on his reindeer. So Santa's there and he's getting around and he's spending time delivering these presents. How does this happen? Well, this has been elaborated in a fantastic book here by Gregory Moan, The Truth About Santa. And the problem here is, even if he does get extra time at each location, at 500 million homes, say 5 seconds per home, a year is about 30 million seconds. This takes Santa about 80 years. And we've seen by various arguments, parallel universes, copying by drain holes, there must be a multi-parallel Santa. So how many Santas at 5 seconds per home? Well, we don't know. We don't know. But if you take a conservative estimate of, say, 200 Santas, then 80 years times 12 months over 200 Santas, that's 5 months per Santa. That's kind of a full-time job and then that sort of makes sense. So this is a good back of the envelope estimate for the number of Santa clones that we must need to have by one method or another. On the other hand, it seems to be too much physical work for each Santa. One sack before he reloads through the wormhole. So I imagine a whole network of wormholes where he's just stepping through and going into the living room, steps through again, goes through into another house and so on. And his sack gets lighter and lighter, and eventually he just reloads at the North Pole. So with about 30 presents per sack, we have a sack that weighs about 15 kilograms. At 5 seconds per home, and keeping in mind that he reloads the sack, so the sack's getting maybe linearly lighter, that's the factor of a half in my power estimate. We have that the power that Santa's outputting here at MGH, he's got to lift the sack. He does this on average about every 5 seconds. That's pretty low output, 15 watts. But keep in mind, he has to do this for all day. I mean, so his daily output, 15 watts times 12 hours, 3,600 seconds per hour. This gives about 650 kilojoules for his daily work output. If we look at a weightlifter doing a power bench press of 220 pounds and ask what the power output of this weightlifter is, again, our mgh over t gives us a much larger number, 500 watts. How long would he have to do that for to be doing the same power output of Santa? That's 40 minutes. That's a pretty rigorous workout. And it's just not like the Santa we've come to know and love. So there's a real problem here with Santa has to do too much work if we just consider the lifting involved. So the weight must be reduced. In addition, he has to build all these presents on such a short time scale. You know, he may have just become aware of who needs to get what. And, you know, even with an army of elves helping him, you know, we realize that that is, in the physics terminology, hard. So the presents have to somehow manufacture themselves. And so Santa needs his presents to grow overnight inside their initially empty gift boxes. And here we turn to the phenomenon of self-assembly, which comes to save the day. So the idea is, and again, this is speculation. I haven't spoken with Santa about this, but it is to let biology do the work and build the presents. If we take a tree, for example, it starts from a tiny, tiny little seed. It executes a genetic program to convert a seed into a large, well-defined structure. In some organisms, like C. elegans, a small nematode, the time and position of every single cell and the generation of it, where it maps to, where it ends up, for every one of its 1,033 cells has been mapped. So this is just showing you the fidelity of that genetic blueprint and how it can basically be utilized, co-opted to manufacture a present, a genetically engineered present. Even cells, you can see organized nanostructures down to the nanoscale. And even almost sub-nanoscale. This is a nanoscale, a picture of a piece of a ribosome, for example. So where to get the materials, where to get the energy? Well, the proto-presents can breathe in carbon dioxide through the air. They can take in water vapor. There's plants that can grow on just water vapor. Why not presents? It's interesting that we leave them under the tree where there might be extra humidity that the presents could incorporate into their growth process. Where do they get the additional water and energy sources? It's interesting also we leave out milk and cookies for Santa. Do we really think he's eating 1 billion milk and cookie dishes? It's doubtful. He'd be a lot bigger than he is. So it's quite feasible that these milk and cookies would be used as energy resources to grow these presents. They may take radiation from the fireplace. It's all basically adding up to make self-assembled presents. You might argue Barbie dolls are made of plastic, for example. So, you know, that's not really what we think of when we think of a biological material. But, you know, think about it. A Barbie doll is made of plastic. Plastic is made of hydrocarbon chains. Hydrocarbon chains come from naphtha and crude oil. Where does crude oil come from? Trees and plants. So it's totally feasible that one could grow a Barbie doll through an organic living skin that enzymatically manufactured the plastic in its extracellular matrix. And here to kind of show how that might work is this self-assembling Barbie mermaid. And after growth is complete, the skin would undergo apoptosis, much like the webbing in our fingers undergoes apoptosis, and basically dissolve. So we don't see the biomembrane after growth is complete. For metal toys, I suspect Santa must hate these. He probably has to put the raw materials in the box or maybe transfer them through wormholes. But the upshot here is that we have genetically encoded, biosynthetic hybrid, self-assembling toys. So in closing, who is Santa? Is he the lucky altruistic recipient of alien technology, as we must hypothesize? Perhaps it seems the most feasible explanation, or perhaps he's just a brilliant physicist hiding in plain sight. Thank you.
Thanks, Steve.